The population of a Midwest industrial town decreased from 210,000 to 205,000 in just 5 years. Assuming that this trend continues, what will the population be after an additional 5 years? So in this example, we're going to assume a population decay model. I'm calling it a decay model because our population starts at 210,000 and decays to 205,000. And we want to use the population decay model, which looks like this. P equals P naught e to the kt, and P naught stands for the initial population. K is our decay rate. I've already mentioned that this population is decaying. If the population was growing, we would call it a growth rate. And this value of K will come out to be negative because this is a decaying population. Then we have T, which is standing for time. And then we have our P, which is our population after time. So with this information at the beginning, that we have a starting population of 210,000. After 5 years, it decreased to 205,000. We'll be able to find that decay rate. So we're going to use P naught to be 210,000. We're going to use P to be 205,000. And we'll use T to be 5 years. So we're going to substitute those values into our exponential decay model. And that will give us 210,000 equals 205,000 e to the k times 5. This will allow us to solve for the value of k. That value of k is in the exponent. So we're going to solve this exponential equation by isolating the exponential portion. We'll isolate it by dividing both sides by this 205,000. And I apologize, I substituted that incorrectly. So let me correct that now. Why don't we just start that portion over again? Since I did that incorrectly. We have an ending population of 205,000 and a starting population of 210,000. E to the k times 5. So we're going to solve for that value of k, which is in the exponent. So we need to solve or isolate this exponential portion. We're going to divide both sides by 210,000 so that we can isolate that exponential portion. These cancel out, and I'm left with e to the 5k on the right. On the left, these zeros cancel each other out, and I have 205 over 210. We could probably reduce that a little bit further. Both of them are divisible by 5. So 205 divided by 5 would be 41, and 210 divided by 5 would be 42. So we have 41 over 42. We're going to continue to solve this exponential equation The methods we typically use are relating the bases or trying to make the bases the same, which we can't do in this example, converting to a log, or taking the log of both sides. We can do either of those methods, and I prefer to take the log of both sides. I'm going to apply the log on the left and apply the log on the right. I'm using natural log. And once you introduce the log, then you're allowed to use log properties. And the one we're going to use here is called the power rule. And the power rule allows you to pull that power into the coefficient on that log. So we have 5k natural log of e. Natural log of e is 1, so this becomes 5k. And then I can divide both sides by 5. And I have k being natural log of 41 over 42 over 5. Let me make this correction over here. I wrote 24 instead of 42. So we can get a decimal approximation for this value. And you'll see when we do this calculation that this value of k, the decay rate, will be negative. Got natural log of 41 over 42, and then divided by 5. And we've got negative 0.00, we'll round to 3 decimal places, negative 0.005. Although I found this decimal approximation, I'm going to use the exact value here because I had to round to write that decimal down, and I don't want the rounding on this decay rate to cause rounding error on the second part of this problem. So taking a look at the question that is posed in the second sentence, it says, assuming that this trend continues, what will the population be after an additional 5 years? So there are 2 ways we can approach this calculation, and one of them is if we use P naught to be 210,000. If we use 210,000, then our time will be the original 5 years plus the additional 5 years, which would be a total of 10 years. Or we could choose to use P naught as 205,000. And in that case, we would only need to use the additional 5 years to do the calculation. So we're going to substitute these values of time, the initial population, and the value of k that we just found into our model. So our model is P equals P naught e to the kt. And we can substitute these values in 210,000 e to the natural log of 41 over 42 over 5 with a time of 10 years, so times 10. When I type this into my calculator, I like to write the time in the front because I don't have to use as many parentheses that way. So I would write e to the 10 times natural log of 41 over 42. So this right here should say 42. And if I was going to use the other option, I would write this as P equals 205,000 e to the 5 natural log of 41 over 42 over 5. And I left off the over 5 right here, so hopefully you caught that. I forgot this right here on the other one. We're going to type these values in the calculator to get the population after an additional 5 years. So I would type for the first one 210,000 and e to the 10 times natural log of 41 over 42, and then over 5. So with an additional 5 years, our population is now 200,119. And we can do the other one just to confirm that it'll come out the same. So 205,000 and e to the 5 times natural log of 41 over 42 over 5 gets me the same 200,119. So for this example, if the trend continues, the population will reach 200,119 with an additional 5 years. Thank you for checking out my videos. Have a great day.